we continue our discussion of infinite series. In this video, we look at the integral test. As a motivation for the integral test, let's take a look first at the following infinite series. The infinite series n equals 1 to infinity of 1 over n squared. Does that series converge or does it diverge? Well, let's see. Let's start by listing out the first few terms in our series, just to kind of get an idea of what this series looks like. Let's let n be 1, and n be 2, and n be 3, and n be 4. And let's list out the first 4 terms in this series. When n is 1, I have 1 over 1 squared, which is 1. When n is 2, I have 1 over 2 squared, which is 1/4. When n is 3, I have 1 over 3 squared, which is 1/9. When n is 4, I have 1 over 4 squared, which is 1/16, etc., etc., etc. In fact, this is the series that has the perfect squares in the denominators. Now, this series has terms that are getting smaller and smaller and smaller, right? So the terms are getting smaller, they're heading to 0, so it's very possible that this series converges. The question is, do those terms get small enough fast enough? Well, let's see. 1 over n squared reminds me of a corresponding continuous function, f of x equals 1 over x squared. And how does it relate? Remember, f of x equals 1 over x squared is defined on all real numbers, so it has a continuous graph, whereas 1 over n squared, that is defined only on integer values, the positive integer values. So I'm going to go ahead and I'm going to graph the function 1 over x squared first. Remember, 1 over x squared is a rational function. It has asymptotes along the x-axis and the y-axis. And if I put some specific values in there, 1 maps to 1. 2 maps to 1/4. 3 maps to 1/9, etc., etc., etc. So this is the function f of x equals 1 over x squared. Now I'm really only concerned about the positive side, so I'm only going to look here on the positive side. And what if I was to do as follows? What if I was to actually take and look at the inscribed rectangles that correspond to this function? What do you observe? Well, notice the width of each of these rectangles is 1 unit. Do you see that? The distance between each of those integer values is 1 unit, right? So the width of each rectangle is 1. What about the height? Well, this first height is 1 unit. It's the y value that corresponds to the x value of 1. The height of the second rectangle is 1/4. That's the y value that corresponds to the x value of 2. The height of the third rectangle is 1/9. That's the y value that corresponds to the x value of 3, etc. So what if I was to look at all of these inscribed rectangles? Let's compare that to, over here, the infinite series that we started with, and what do you see? This is the value 1. This is the value 1/4. This is the value 1/9. This is the value 1/16. There's a direct correspondence, isn't there? So let me go one step farther and look at the following. If I was to take this spot here and look only from 1 to infinity, what could we say? We could say that the area of those rectangles, so the area of the inscribed rectangles from 1 to infinity is less than or equal to the area under that curve. When you agree with me, that's actually less than or equal to the area under the curve. And how do we represent area under the curve? We use it with an integral, right? The integral represents the whole area under the curve. So those green inscribed rectangles have to be less than or equal to that from 1 to infinity. And that then lets me make even a broader claim. I have that the infinite summation n equal 1 to infinity of 1 over n squared, which equals 1 plus 1/4 plus 1/9, etc., 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 is less than or equal to 1 plus the integral from 1 to infinity of 1 over x squared dx. It has to be. And what's great about that? Well, now we're going to go back a couple weeks or longer. We solved these. What are these called when we have an infinite limit? This is called an improper integral. And we know how to solve improper integrals. And I don't know if you remember, but we did say something special about these types of improper integrals. But let's go ahead. This is an improper integral. We know how to solve it. So let's figure out what is this improper integral. Let's actually work this out. The integral from 1 to infinity of 1 over x squared dx is rewritten as the limit as b goes to infinity of 1 to b of 1 over x squared dx. Let's evaluate this antiderivative here. And so let's going to take the limit as b goes to infinity of, this is the antiderivative from 1 to b of x to the negative 2 dx. And we evaluate that by adding 1, dividing, doing our power rule, and that gives us the limit as b goes to infinity of negative x to the negative 1 from 1 to b. And continuing, that's equal to the limit as b goes to infinity of negative 1 over x from 1 to b, which is just the limit as b goes to infinity of negative 1 over b plus 1 over 1. Carrying on, as b goes to infinity, what can we say about 1 over b? Well, negative 1 over infinity, as b gets infinitely large, this heads to 0. And so that tells me that this limit is just 1. If we have an improper integral that ends with a limit that is finite, what do we say? We say that the integral converges. But more than that, what we started with was we started with the infinite series n equals 1 to infinity of 1 over n squared, and we said that that was less than or equal to 1 plus the integral from 1 to infinity of 1 over x squared, which we discovered was 1, and that means the infinite series n equals 1 to infinity of 1 over n squared is less than or equal to a finite number 2. That means it's bounded above, and because it is bounded above by a finite real number, that means this series converges. This series converges. Where does that help us? Well, it gives us a motivation. It kind of tells us exactly what the integral test is going to tell us, which is the integral test. suppose that you have an infinite series with positive terms. Moreover, suppose that there exists a function, f of x, and a positive integer n, such that the following three conditions are satisfied. Number 1, f is continuous. Number 2, f is decreasing. And number 3, f of n equals a sub n for all integers n greater than or equal to capital N. Then we can make the following conclusion and the following statement. The infinite series n equals 1 to infinity of a sub n and the integral from capital N to infinity of f of x dx either both converge or both diverge. Really, we take a series, we take its corresponding function, whatever that improper integral does, converge or diverge, tells us what the corresponding series will do. Let's complete this video by using the integral test to show that the harmonic series 1 over n diverges. Let's start by looking at the series n equals 1 to infinity of 1 over n and writing to it the corresponding function f of x equals 1 over x. Now there are three conditions that have to be met in order for the integral test to apply. The first condition I want to check is my function f a positive function? The second thing I need to check is that function decreasing? And the third thing I need to check is this function continuous? And we specifically are going to consider values starting at 1 and going to infinity. So we need to make sure that f is positive when x is greater than or equal to 1, that it's decreasing when x is greater than or equal to 1, and that it's continuous when x is greater than or equal to 1. So, are these conditions true? What do you think? Let's see. Let's investigate. F of x equals 1 over x. What can we say? Well, this function is continuous everywhere except what value? X cannot be 0, right? Otherwise, this rational function is continuous everywhere. But our domain specifically is x values greater than or equal to 1, and so x not equal to 0 doesn't even matter to us. Yes, our function is continuous, x greater than or equal to 1. It's also positive, right? Because if I put a value in here that is greater than or equal to 1, that means I'm putting in a positive number, correct? And if I take 1 divided by a positive number, well, that's still going to give me something positive. And so f is also always positive from 1 to infinity. And how about decreasing? How can we show if a function is decreasing? Remember, we're focusing right here on f of x equal 1 over x. Well, I can think of two ways. The first way is to visualize it. F of x equals 1 over x is a very simple basic rational function, again with asymptotes at the x-axis and y-axis. It's an odd function, has symmetry about the origin. But more importantly, what do you observe? F of x equals 1 over x from 1 to infinity does what? It decreases. This function's decreasing. So visually, we see that it's decreasing. If we don't have that visualization, what's another way? Another way would be to look at the first derivative, right? Recall that if we take a first derivative and it's positive, that means the function is increasing, and if it's negative, that means the function's decreasing. Well, what is the first derivative of 1 over x? The first derivative of 1 over x is negative 1 over x squared. And what is x squared? X squared is always a positive value. And so a negative divided by a positive is always negative. My first derivative is always negative. Therefore, that means that my function is always decreasing. So that's a second way to check. All right, now that our conditions are satisfied, now we actually get to do the integral test. And I often find that this is the hardest part, checking those conditions. Now we simply look at the integral test, which says that our series will do whatever the corresponding integral will do. So let's look at the integral from 1 to infinity of our corresponding function 1 over x dx. This is equal to the limit as b goes to infinity of 1 to b of 1 over x dx. What is the antiderivative of 1 over x? That's the limit as b goes to infinity of the natural log of x from 1 to b. And so that means I'm taking the limit as b goes to infinity of the natural log of the absolute value of b minus the natural log of 1. The natural log of 1 is just 0. What happens? The natural log of b as b goes to infinity, so as b grows infinitely large, what happens? That's just infinity, right? This whole limit goes towards infinity. And what does that tell us? When we have an improper integral that ends with a limit at infinity, that tells us that the improper integral diverges. And the integral test that we're just learning tells us if the improper integral diverges, that means the corresponding infinite series diverges. So let's make our conclusion. Using the integral test, we see that the harmonic series does in fact diverge. In the next video, we will do another example demonstrating the integral test and how it is used to show convergence or divergence of an infinite series.